Hello and welcome to our tutorial. Today we're going to be talking about how to use an Agilent PFA project file directly with FluoroMatch and in the future LipidMatch and PolyMatch as well. And so we'll open up our software first. So 5.64 and later support the PFA projects. And so you'll see that there's a redesign of the interface in 5.64 compared to previous versions. And in this section over here, you'll see PFA plus mzML for Agilent only. And so this is where we're going to import our project file, our PFA project file. You can import negative data, positive data, or both. A single PFA file is like a zip file. It has all of your chef files for all of your samples, all your extracted MS1, all your extracted MSMS, your feature table, annotations. All of that will be incorporated into FluoroMatch when you have that PFA file. So one positive, one negative PFA file, or both a positive and negative PFA file. And then you'll also need mzMLs directly from Agilent Qual Browser that you can export as well. And this is for the MS1 data only. You only need a few reference files. I'd say at maximum 10 reference files. These are just going to be used to visualize your EICs as you click through the visualizer, as well as to visualize the entire MS1 spectrum, not deconvoluted. You'll get a deconvoluted MS1 spectrum from the Agilent file itself. So, with all that being said, let's go into some example data. So here's a .pfa file. In our previous tutorial video, we showed how to generate these PFA files. So let's grab that PFA file and drag it into the correct section over here. If you scroll over, especially if this video, if the text is too small, you can scroll over these boxes and a tooltip will come up that describes exactly what you need to put in each section. Notice that now all these other sections and many of the parameters grayed out that aren't relevant for the PFA file. Now you'll also need an mzML file. Again, just one is fine for EICs and MS1s, but if you want to visualize EIC and MS1s across multiple samples, you can include those as well. I'm just putting one in here. I'm also going to put the positive mode data in. So I'm going to drag a positive mode PSA as well as the target PSA file. Sorry, PFA. And so now they're all in. And then just as before, we'll choose our output directory. And it'll generate free files into the directory. And then we'll include our project name. All right. And choose your parameters. So since you're using an Agilent instrumentation in this tutorial, because this works only for Agilent instrumentation, there's two parameters you can check that have been very well optimized for Agilent. So 6546 and after is what I use for the 6546 and the Revenant. You can also use this parameter for other prior instruments. The only difference is the ppm mass tolerance. So sometimes in prior instrument models, you might get things that move out of a 5 ppm or 0.005 Dalton window, and so we try to capture that. But in the 6546 and afterwards, the mass accuracy is really stable on these Agilent instruments, so we could stick to same mass accuracies as we get in an Orbitrap, so 5 ppm, 0.005 Dalton. And now you'll click Start once you select your parameters. Note that the blank filtering is not enabled at this moment, but we left it not grayed out because we'll enable it in the future. So if you want to remove features that are from your blanks, either do that prior when generating the PFA file, or if that's possible, or you can do it afterwards in Excel. So now you click Start, and at this moment, I believe all the loading bars when we release it will go up. At this moment, only this loading bar will go up, and when it's done, it should look like this over here with a full loading bar, and then you'll get this text, this message at the very end, no matter what software you're running from the Match series. It says software complete, congratulations, now upload all necessary files into the visualizer, etc. So that will be available to you. Let's get out of here when you're complete. So now you can see the process of the software, and so it's now reading in those chef files. So built into FluoroMatch is a way to generate the chef files into an R object and then also into a CSV object. And therefore, if you do need to convert chef files into R objects or CSV objects for any other programmatic reasons, know that we've built tools for that as well. So here you can see that it's now parsing the data and doing MS1 generation. So it's extracting the MS1 data and reformatting it into the format that FluoroMatch needs. It will also do the same thing for the mzML data using the MSP file in the PFA. And then also generate a feature table from the chef files as well. Now, while this is running, we can talk about how you generate those mzMLs. We do talk about that in separate tutorial videos, but since you'll need an mzML file here, you can go to the prior tutorial video to see how a PFA file is generated and some suggested workflows for PFAS. We go into Qual Browser, and we open up some .d files that have the MS1 data that we want to visualize the ESCs and MS1 for. And then you see this export mzML options over here. This is going to be under the method editor. So if you don't see it, go to View, Method Editor, and you should be able to see the Export mzML option, and you just click it and then select the files that you want to export. There are parameters over here. The recommended parameters I have are centroided. I leave these, as you see here, 2 and 0.7 for the maximum peak width and required valley, respectively. Absolute height, I like to put it at 100 counts or more. That's what I like to cut off for my MS1 spectra, and I do not cut off relative height. That's very important. So by default, this relative height may be selected. It will make the file smaller, but this is saying if something's 3 orders of magnitude lower than the main peak, remove it, but our PFAS are often going to be 3 orders of magnitude lower than the main peaks in the MS1 spectra, and so it may remove all the PFAS. Same for any types of analysis where there's a trace species among very abundant signal. So take the relative height off. And then I do an unbiased isotope model because for PFAS, we have very unique isotopic patterns. And then again, you would click export and export them, and you'd get the mzML files that you can just drag directly. Those mzML files, as with all FluoroMatch, should have correct naming conventions. So it should be _pause.mzml and _neg.mzml. I like capital N, eg.pfe, capital P, lowercase os, .mzml for the neg and the positive, but capital L's don't actually matter. That's what I usually use, just so that you don't get as many errors. All right, so you can see that it is continuing to work. It will tell you how many compounds it found, so 4,000 plus compounds. It wrote the MS1 file, and then it's now generating a feature table, and then it finished generating the compound list. And so you can watch it go step by step as it parses these chef files. When you're done running the software, it should look almost identical to the outputs that you're used to from if you've run FluoroMatch or LipidMatch or anything before without a PFA project file. So you'll get the same, you'll get an annotated folder. Here's one that's already finished. So you'll get this folder. This is slightly different than you're used to, only in the sense that it also has the PFA file will be moved here. So it'll also be in this project, just so that you have it there as well. You'll have your feature table, and then you'll also have the unzipped chef file that has all the different files that are within your project file. And then in your outputs, you will get your final outputs. So here's your neg-id fin file, and if we open that one up, again, very similar output as before, so I won't go, we have separate tutorials that go over the FluoroMatch outputs. The only thing I did want to notice here is that these adducts that you see over here, these are from the PFA file itself, as well as from identifications and things of that nature. And here you can see the adduct that's from the PFA files. You can see that the M ion, so the molecular ion, is also contained. And so this is going to be the compound level information with volumes, taking all those adducts into consideration and all the isotopes into one peak. You'll get your FluoroMatch identifications as normal, and then your peak areas or peak volumes are going to come from the PFA file itself. So these are from Agilent's peak picking, and then you do get some of the Agilent metrics alongside that can be used, and you can use these in the visualizer as well, which we can discuss on a future video. So here's the MFE score, find by formula score, any identification. So if you run your identification using the Agilent ecosystem, those names will actually be carried over into this file. So you'll both be able to see what FluoroMatch annotated, but you'll also be able to see what the Agilent ecosystem, what you're able to use to be able to annotate the compounds as well. You'll also get the formula from the chef file, the overall score, the database match score, and all the different pieces of information that came from your chef file. So the CAS registration number, any other identifiers, such as inch key. All of this will be carried over from the chef file. And then you can also visualize that in the visualizer. So the idea is that we're merging the ecosystems between Agilent and our open source FluoroMatch and other software such as LipidMatch and PolyMatch. So I'll close that and then just briefly open up just a sneak peek, but we'll go into the visualizers in a separate video. but just a sneak peek, is as prior, you're going to have a visualization of everything that the Agilent ecosystem was able to pull out, as well as the FluoroMatch identifiers on top of that. Something new in this visualizer system is now that they're sized by the abundances, so either the volumes or the peak areas or peak heights that came from the chef file. And so now you can see the different compounds, their annotations, and their amounts. And note, like, this mzMS data that you see here is the mzMS that's extracted now across all your samples, cleaned up and combined into one sample so that you have a single beautiful mzMS spectra per feature that you can use to identify these compounds. Same thing with the MS1 data is from a deconvoluted one from the Agilent ecosystem from Explorer. And then your formula predictions are done on top of their already deconvoluted isotopic patterns. We have the molecular ions now that you can filter on. So you can pull out all of the compounds. So for example, you can see that this compound and this compound are in-source fragments of each other, with this being the carboxylic acid and this being N-CO2. Which you can see in the extracted ion chromatograms, how they overlap perfectly here. And so in the new software, you'll also be able to filter by those ion volumes. So Agilent already combines in-source fragments, isotopes, other adducts, and so we'll be able to see all of those in one and be able to group them, so instead of having to figure out whether something's an in-source fragment or not. So with that, I'm very excited for users to try and see all the different creative ways that they can use the Agilent ecosystem and our matched ecosystem and combine the benefits of both. And please reach out. Thank you.